Okay. Good afternoon, everyone. Today we have two invited speakers for AGEA seminars. So the first speaker is Professor Yuan from Capital Normal University. She will talk about rank zero Segre integrals on Hilbert schemes of points on surfaces. Okay, now please.
Okay, thanks for the organizer for the invitation. So I will talk about rank zero integrals on Hilbert scheme of points on surfaces. So first, I will talk about the problem. What's the problem and my results. Then I talk about strategy and also the sketch of proof. So maybe this talk contains is a bit technical talk. Okay, so the Hilbert scheme of points. I think this is some well-known facts. So now we let S be a projective surface with complex numbers. Now we denote by Sn, so the Hilbert scheme of endpoints. So also Sn parameterize you can look really at zero-dimensional subschemes of S. Also points of Sn is also rank 1 ideal shapes of colons and we have a universal family. So so now we have this diagram. We denote by Pn and Qn these two projections, and we have this universal family. Okay, this is a closed subscheme of this Sn times S. So they're all well-known facts, I think. So we have a okay. We have a special class on this Hilbert scheme of points. So now we get select this Kx with a Gaussian group of coherent shapes on X. Now we have a group homomorphism. So from Ks to this Ksm. From we denoted, so for every alpha we denote alpha n upper n to be this class. So now you have this diagram. So you have this diagram. You pull back alpha with this Qn, and you tensor it with this structure shift of this universal family. So you do the flat tensor, and then you push forward with this Pn. You have to take the derived push forward, certainly. So this here is the flat tensor, dot. Yeah, and here is this one is the derived pushback, push forward. If alpha is a class of vector bundle, so this is only the restriction. So pullback of the alpha is also vector bundle, and you restrict this bundle to this subscheme, and then you push forward. And you can see that since this Pn is it quantifying it, you don't have a hierarchical direct image if you have really a subshift over this this universal family. So Pn itself is not fine quantifying, but Pn restrict to this universal family is quantifying it, right? So if alpha is a vector bundle, so it's a class of vector bundle, then we can see that this alpha n is just so you push forward it. You don't here you have exactly the tensor, and here you only have this push forward. You don't have high direct image, and this one is so you then you get a class of a vector bundle of rank nr. Now, Segre integrals is just defined to be the integration of the top Segre class of this of each alpha n. So S to n is the top Segre class for this alpha n, and then you do the integration. So, if you view this the top class, you also can consider it as you're counting the points. So this is it should be 0-dimensional, so you can count points, so the number of points. Okay, so then we put everything together. So now we let this n start from 0 to infinity. So when it's 0, then everything is empty. And we let this integral to be 1. So this series starts by 1. Okay. And then we have this Segre series defined as follows, very clear. This we have to compute this Segre class. We have this. Okay.
Sorry, Yao.
Yes. Yeah.
So this series is always well defined, or it has a limit, right?
You just have to you define it as formal theory. But for some cases you can show.
Just define formally, right?
Okay. Yeah, formally. Yeah, formally. Just form series. But somehow they have showed that this should be some function. So I always talk about this theorem. So yeah, I don't know why I have this. Okay. So now we have a look at this theorem. Theorem is due to the Linz-Root, Gotcha and Lane in 2001. So it said this theory can be written in this form. So now you can see that, but here we have A0, A1, they are also formal series. Okay. So it's not know yet whether they're all rational functions. But now, so I will talk about so the A0, A1, A2, A3. I think they are all known for they are explicit form now, but still A4 is something unknown. Okay. So the theorem says that there's 5 universal series. So these 5 universal series only do not depend on the surface, but depend on this alpha. So only through the rank. And also certainly this integral itself depends on the first Chern class and second Chern class, but it should have this form. So you have a first Chern class here and here, and the second Chern class. Also, it depends on surface certainly, but certainly gives contribution to this here. Okay, you can see. Okay. Okay. And so these formulas for at firstly for the class of line bundles. So you have rank 1 and there's no second Chern class. Lane conjectured the formula for this A1. So now if you have a second, now we can see this formula right here. Now for a class of line bundle, you don't have the second Chern class. So you don't have this A0 term. And now you can the lane conjecture the A1, A2, A3, A4 for rank 1 case. Right. So you can also choose another element class of rank 1 sheaf, but with a second Chern class, not 0. But they still have A1, A2, A3, A4 should coincide with this line bundle case, since this universal series only depend on the rank. So Lane conjectured the formula for this A1, A2, A3, A4, and Marian, Oprea, Panda proved Lane's conjecture. They actually computed A0, A1, A2 for all ranks. So they have this A0, A2, A3, A4 for rank 1, and A0, A2, A1, A2 for all ranks. Okay. Here is their formula. It looks not that complicated. So this rank is S and R is the rank plus 1. Okay, the rank R plus 1. So here this notation is not so it's a bit different. Okay. We can see that they're not rational. For fixed R, they're not all rational functions actually, right? So you might have this might not be an integer, right? But still, this expression, those expressions are not so complicated. Then you also do a change of variables. So you have z here and you have t here. You do this change of variables. I would like to talk about this polynomiality. So actually, how this Marian operator Ponte prove this theorem? So they choose as we can guess, since we don't have A3 and A4, probably we'll do something on this canonical line bundle on surface with a trivial canonical line bundle. Yes, so they do something on this K3 surface. This prove the theorem by computing the series associated to a vector bundle with small deformation space for as a K3 surface. So now we can see that so you choose a vector bundle, then you have a positive rank, right? But the theorem is about for all ranks, okay? Right, so why we can conclude this statement for all ranks because we have this polynomiality. So it is also this theorem. And maybe we look at this one. Okay, so also the theorem by Alinsud Gotcher-Lane in the same paper as last same theorem. So for each m for positive integer, there is a polynomial. So in this rank, first chain class, second chain class, canonical line bundle, and also the chi-OS independent. This polynomial itself is independent of the surface. Okay, the contribution of surface is in this canonical line bundle and this chi. Okay, so there we have this polynomial. So for each circle cross, so it should be a polynomial in this rank R. So in the rank. So once you have this polynomial equal to some polynomial for all rank, for infinite many rank, then this polynomial can be determined. So that's polynomiality. So then you get this formula. So you get this these all expressions for all ranks. Although you only compute it for positive rank, right? So now by this theorem, once you obtain the A0, A1, A2 as functions of R for infinite many R, then equal to those functions for all R, then you get the statement for all R. So that's how they get. Yeah, actually, you can imagine that if you have a vector bundle, it should be how say the relatively easier to handle.
Wait.
Yes. Yes. So, any question? Well, okay. So let's go on. So they also, so the Merriam operator Ponte also in their paper, they also give explicit visit formula for A3, A4 with rank two case. So rank one is so conjectured by Lane, and they prove it first, and then you and then also prove the computed this A3, A4 for rank two. So now it is already know for. So the whole series determined for rank two. But for rank two, the results seems very complicated. There is some algebraic, so there are algebraic.
Sorry,
Yes.
Yao. So I suggest that you don't have to keep the screen moving so fast. It will give some.
It's supposed to be some
problem.
PPT, but I don't know why it doesn't go that way. So I have to. Yeah, I don't know why. It should be
So
some.
why don't you use page down like something rather
Yeah,
than
but
use
I don't know. There's no page down. I page down. I don't have this page down.
Okay.
Okay. Maybe. Where am I now? Sorry, I don't know. I should have this page down, but I don't. It doesn't work. So it's not a PPT. I get confused why this. So maybe I try to see why. Okay. Okay. now it works. Okay. So now here we are. Okay. So they also give the explicit formula for rank 1 and rank 2. And how about rank 0? So they give a conjecture. So rank 0, we already know A3, A. So there are 5 series, right? So we already know this first 3, and there are there are 2 left. But for rank 0 case, we have this change of variables. We have this by the theorem, we have this expression. Now we need A3 and A4, then we can determine this Segre series. But A3, A4 is very easy to get. Actually, you can let alpha to be 0, right? So it's rank 0, so everything is 0. Everything is 0, so this series should be 1. And you have A4 should be 1. Okay. And since A4 only depends on the rank, so it's always 1 for rank 0. Now, how about A3? So this they give a conjecture. So in rank 0, we have this formula. Okay, not complicated, right? Seems very nice formula. Yeah, that's so our result is we prove this conjecture. So that's our main theorem. So we choose the
sorry, Yao. So there is no expression in terms of zeta, right? So I don't.
Yeah,
so
you have to
why
do the change of variables.
Okay. So no beautiful expression in terms of zeta, right?
No, you want this for then you do yes, right? You have it. Yeah, it will not be that nice if you want to write it in a function of z.
Okay.
Since then you have to solve this equation, and yeah, it will not be very nice. Yeah, actually, yeah, is so part of this. I think part of their skills that you choose the right change of variables. Otherwise, you get a complete mess. Okay, so our result is we prove this conjecture. So that's our main result. So this we just since there are universal series, so we only choose one surface. You fix the surface and you compute the Segre series. You get the whole Segre series for a chosen surface. Then you get all these series actually. Since they are universal, they don't depend on the surface. So I choose the surface to be the P2. So yeah, very easy. Yeah, and we choose this class of this anti-canonical class divisor. Okay, so we have this a curve. So we curve of this class, so minus KS. So we take this class of the structure sheaf of this curve. So it's a rank 0. And we compute this Segre integral. They're all 0. This is our main theorem. So they're all 0 for all n. Now we can show this Segre series. So we write down.
So sorry, yes? Sorry, excuse me. So so the rank is rank of the vector bundle or
rank of this class? Yes,
rank of the class. Okay, not
yes.
vector bundle. Okay.
No, it's not always the vector bundle. The rank can be any integers. It's not even positive. It can be negative, right?
Okay. Okay.
You always have this class, and you always can define this class, and you can also do this integration. And here I choose some typical rank 0 class, and I compute all these Segre integrals, and then I got this Segre series, and then I can get their conjecture. Yeah, so you just put everything together. So now since the A3 is the only term we don't know for rank 0, right? So we have A0, A1, A2. So by Marian operator Ponder-Ponder's theorem, you let rank to be 0. And we get A4 by letting alpha to be 0. So it's easy. So now the A3 part is only same. We don't know. And we get, so for this special case, we get this Segre integrals. Segre series to be 1 equal to 1, right? Since we have other terms, all zeros. So we have this one. So you by their theorem, so by this universal series, so you put everything together, you get these things. Yeah, so this is corollary, right? So this corollary proves their theorem. So now you get.
The last line doesn't show very well.
Why? So the last time is just the theorem. So it's just this statement, right? Okay.
Okay.
So how we use this theorem to prove this theorem? The conjecture. So I will explain. So it's not difficult. It's very easy. It's very direct. So you compute. So now the series depends on the C1 with the second number with of C1 with this canonical line bundle. So you compute everything together. So for this special case, right? So we choose this special case. So S is P2 and alpha is a class of structure shift of curving this anti-canonical line divisor. Okay, so now we can compute it 0, 0, or 9. So we get the Segre series. So we have so the Segre series for this special case is just equal to 1. And on the other hand, with this theorem, it should have this expression. So we get it should have this difference with some roots of unity. But this mu should be 1 because this starts with our power series beginning with 1. So that's part of the theorem actually. So we have the final statement, so which proves their conjecture. Okay, so that's our main theorem and implies their conjecture. And yes, soon after I got this result, and also I got this result soon after I got this result. I also see that Gaucher-Meili get a more general result. I will also mention their result. So very recently, I think last month, so they also put some a paper on the archive. They use localization to compute the Segre series. So you have a toric surface and the class of toric vector bundle. So here you see they also do this vector bundle case. So yeah, the rank no bigger, no smaller than 3. Okay, they prove the following theorem. So you can see this. So you have with also the change of variables, and so it's a bit complicated. But we have a polynomiality, right? So once you get this expression for infinite many R, then you have this relation for OR, right? So this theorem applies to A3 for OR, right? So you have it here, what you are computed is for R no less than 3, but actually the result applies to OR. So it also applies to rank 0, right?
So what is X?
X is not important. X means this here. You get this formula, this polynomial, and take the part of the coefficients of X0, right? You have this polynomial, not polynomial. This is some infinite series, but so you have this infinite series, and you take the X0 coefficient.
Oh, okay.
So X is not important. It's just some variables here. So you can sorry. Once you let R equal to 0, so this 0, 0, well, you can compute, then this term is 1, you get 1. So this total 0 or 0. So their theorem also implies this equality. They actually give all the formula for A3 for rank, right? Okay, but still, as I will talk about my results. So because I So we have a different method, right? They do this localization and they choose, they compute this segregated series for rank, for positive rank case. But what I did is I compute this segregated integrals for rank 0 case. I exactly do this case. Okay, I don't use any localization, although my surface is toric. Okay, so I talk about my results, my strategy. So now S is the projective space. So now we have this incidence variety. So parameterizing all pairs. So you have one endpoints and then n plus 1 point satisfy that it contains the endpoints. So you have this one. But first, so then you define this. So it's you do the projective. So the approach for this idea shift. So this idea shift is for generic points. So the idea shift is rank 1 for generic point here. So this, so you want to do the project for rank 1 line bounded, there's nothing. So this one, so this PIN is somehow should be birational to this Sn times S, right? Then we have this one. So this is exactly this incidence variety. And we have two classifying morphisms, sending the ideal shifts of n point to this Sn and the ideal shifts of n plus 1 points to Sn and plus 1. So they're very natural definition, right? We have I don't know whether you can see these two morphisms, right? So one is per psi n, another one is phi n. So we use this incidence varieties and we can do this induction, right? So you want, if you want to compute something on Sn plus 1, then somehow you pull back with phi n and then push forward via this pull back with this per psi n and push forward with this phi n. You get something on this Sn, right? That's a strategy. So now you have this incidence variety. You have here, right? And then, okay, it's exactly something. So it's birational to this Sn times S. Okay, now we have this. We define this morphism. So you pull back. So pull back with this per psi n to this incidence variety, and then you push forward with this phi n. So phi n is of a relative dimension. I think it's relative dimension 2. So you should lose some information once you push forward, right? Something is not 0 before push forward, and then you get 0 push after push forward. That's possible. But once you get 0 dimensional, something of 0 dimensional on this Sn, on this incidence variety, then it doesn't matter once you push forward, right? So this is Chow ring. I use Chow ring since it's isomorphic to this cohomology. Oops. Okay, cohomology ring. So per psi n is generically of degree n plus 1. So once you get some 0 dimensional some class of 0 dimensional, you pull back and you push forward. Since the per psi n is quasi-finite, then you get this. You get generically quasi-finite, right? And you have this this formula. So so in principle, I should write the integration. So integration here, integration here. But for simplicity, I just write the same letters for the integration and the integral and also the class. You can think about the points, or you push forward and you pull back, you get n times 1 times of this, the numbers. So we can repeat this procedure. So So you do it again. Once you reduce the number of the points, right? You from n plus 1 to Sn, and then you to and then you reduce to Sn minus 1. Finally, you reduce to S0, right? So S0 is just 1 point, nothing. And it's enough to, therefore we have you once reduced to S0, but here you get n plus 1 factorial factor of this factor. So our theorem is to show this equal to 0. So it's enough to show you it's 0 after times after timing this times this n plus 1 factorial, right? So it's enough to show you do all this map together, and finally you get some thing in the Turing of S0. This class is 0. So for the R, the class of structure shift. So for our choosing R. So we have a recursion relation. So there's a bit. So now there we have the universal idea shifts. So you pull back all this to this incidence variety times S. So you have this exact sequence. And we have this formula for this for our alpha n. So you alpha n and alpha n plus 1, we have this relation. So that's how we do this recursion, right? You should have some relation. So this the crucial relation for our recursion. So Ln is the tautological quotient line bundle of this quotient. So this one is some project, right? So you have this tautological quotient line bundle. So this this is all from Institute Gauch-Lane's paper. I just copy. Okay. And we denote by Ln this first chain class. And also they prove this. It's also by this statement also due to these 3 people in the same paper. Okay, you push forward. So sigma n is from this incident where relative to this okay. So it's to this Sn times S. So it's just the circle class of the idea shift, the universal idea shift, should say. Okay, so now all we have to do is to compute. Okay, the computation is a bit complicated. So at first we have the Kunis formula, standard. So now since S is P2, so you have this decomposition, right? And we write, so we have this all these chain classes for this universal family. The structure shift of the universal family is exactly the circle class of the ideal shifts. So write it in this form, right? Since we have this decomposition. So this is our notation. So this notation. Now, so we have to say that we got this formula, right? This because we have this this relation, and then we got this formula. And there the so we choose alpha d. So now C is not a curve of degree 3, it should be degree d in this P2. Okay, so now it's easy to see this alpha d, the second class of our is alpha d, right? So on P2 is just the -1 DHT, right? So we get this, so this part is easy to write down. So you have this part. So if once we, now we get this recursion formula, and then we put this formula inside this one, you get all these things. So Si alpha d n plus 1 is what we want to compute, and we reduce this one to compute the S alpha n Si alpha dn. But here you can see that if you take n I equal to 2 plus m, if you take the top circle class, then this term won't contribute, right? This, and so you actually deal with this term. So there's another exact sequence we need, but here we have this or stars, so it's not shrink. So you get stars, and if you want to do it with the Chen class, then you have to prove they're flat or something equal to shrink, right? That's exactly in the lemma says. So here this is flat, this map is flat. So now you can use this star. So pullback, so the shrink is not pullback, it's a flat pullback. And so you have flat, then it's flat pullback. But here this is not flat. So both phi n and this psi n are not flat. But for this special case, once it acts on this ideal shifts, it can be a flat pullback. That's the lemma. So once we get flat pullback, then we can talk about the cycle classes, right? Then you have these relations. Okay, and so what we want is the left hand side, and we have the recursion formula. So, but there is one thing we don't know. So the ln is something we almost know. But those are the O delta. So this diagonal, so structural diagonal. And for P2, now we use the advantage for this surface choice. So now S is P2. So now we have this exact sequence for this the structure of the diagonal. Now we can do the exact computation. Right? Yeah, not that simple, but you can do the computation. Okay, then that's our formula. Yeah, a bit long. Okay, so now we have this formula, but we want to get so want to show this the vanish. So the vanish for the top circle class. So now this is the circle polynomial. So it's the top 10, right? So we have to do the decomposition of fn plus 1 minus n plus 1 n, right? Recall that we have this morphism. So we define the subgroup generated with all the class. Actually, once we did this fn plus 1 n, we get so we not only get the circle class for this in for this alpha n, we also get circle class for the in. So as we have already defined, so this theta, so all these thetas, so with some upper and lower numbers, there are all some circle classes with factors of the circle class of some factors of some circle class of this ideal shapes. So I put together. So here you see I have 0 and 1. If you remember that in principle they should have 2. So for circle class, the decomposition tells us there should be 0 factor and 1 factor, and there's 2. So the factor. But I don't use this 2. Okay, the zeta 2, upper 2, I don't use it since it won't appear. So I have all these things with I define subgroup. The first, they are all the same of this odd zeta. They are all related to the circular integral of the ideal shape. Finally, I have one term. It's a class of what we want. So this alpha n. So this is subgroup generated. Why I use this subgroup? Since once you do this fn plus 1 and n, you do it repeatedly, and you get a lot of those things, zetas, before this circular classes. but still you have only one circle class here, and you have a lot of zetas before it. Okay, then I have about this notations. Yeah, if it's complicated, right? Now we get back to our F. Recall that F is defined by pullback and then push forward. We show that you have this relation, you only get, so you have a theta 0 and a theta 1 involved, no theta 2, theta up 2. And once you do F one time, you increase the number of all thetas. But you may increase theta 0, or you may increase theta 1. And also it's possible that you erase two theta. So you take 2 theta 1 and you get 3 theta 0. That's the case. So the 3, I think there are 4 possibilities. So once you do one F one time, you increase number of all the zetas. And possible, there are only 4 possibilities. You increase 1 theta 0, or you erase 1 theta 1 and you get 2 theta 0, or you erase 2 theta 1 and you get 3 theta 0s, or you just increase 1 theta 1. So there are only 4 possibilities. But once you do all this F, so you do this F n plus 1 n and then F n minus 1. So you do the repeating again, you get some several classes and then you get a lot of zeta before it. But we know that, so we define this delta. Okay, so delta is, so once you get 1, 0, delta theta 0, so delta j is the one you get the number. So the j is the number where, so you get the j times more theta 0, right? So theta 0, if you just increase 1 theta 1, then it's delta 0. Okay, so you have this map, you get decomposition for this map. So delta 0 to delta 3. So theta 0 can at most increase, get 3 increase, the number of theta 0. Okay, so now we get the decomposition for this Fn n plus 1 n. So maybe I just say F. So we want to do this F again and again, and we did do a decomposition. We can write explicitly this, how they act. So what you get. A bit complicated. When you do the hat, you mean you erase this term. Okay, so delta 0, you just add one theta 1, theta up 1, right? Theta up 1. We look up at this upper index. So that 1 you add 1 theta 0, you erase 1 theta 1. I think that you erase theta 1 and you. Well, anyway, so you use 1 theta 1, but here you add 1 theta 1 back, right? So the number of theta 1 remain constant, but the number of theta 0s increase 1. Yeah, it's a bit complicated about the delta 2. So the number of theta 0s increase 2, and the number of theta 1s have to decrease 1. Okay, so also delta 3. Okay, they're a bit complicated. But we have our formula, the theorem. The theorem implies our main theorem. The theorem is about the deltas. So now we don't have F because F we decompose the F. Now delta, we ask this. So this we have this lower index at 2pk, so is equal to the number of the deltas. This one belongs to the d-3 times this Chow ring. So now we can see once we let d equal to 3, that's exactly that's alpha, right? So we have this anti-canonical divided class, right? That's what we choose. If d equal to 3, then this one is 0. So that's our theorem. So why this theorem implies the main theorem? So our main theorem is the third integral. Now we get something very complicated in this, looks like some algebraic thing. Okay, so because we have this map F, we do this map again and again, we do it n plus 1 times, then we get something in this S0, in our S0. So here was scheme of 0 points, just 1 point. Okay, this is our formula. So it's enough to show this is just a multiple of d minus 1. So we want to show this, we do this. So we pull back and push forward. We repeat this progress for n plus 1 times. And finally we get something, we get exactly some numbers, and this number is equal to 0. This implies the second integral should be 0. And this theorem square implies that this number should be 0 for d equal to 3. It's exactly when alpha is a structure sheaf of curves of anti-canonical class. Okay, so it seems a bit very complicated. Why this? So now we have this formula. This is the theorem, but we have f. This is our decomposition for f. So once we do this repeatedly in Fn, so for n plus 1 times, then we should have all these things, all the possibilities. But we only need to consider about all these terms in this theorem squares. That's because once you have these lower numbers, no bigger than the lower numbers is not equal to the numbers of all these delta, then either you get something empty, or you get something contained theta up 1. So you have a theta up 1, but now we are on our S0. S0 is 1 point. You don't have any theta up 1. So all the terms you contain theta up 1, it should be 0 automatically. So now we have only only this term left. So this is exactly what our theorem tells us. But still, this theorem is a bit, to prove this theorem, we needed to do something still very complicated. So we have theta 0, theta 1, theta 2, theta 3, and we have this proposition. Okay, this proposition implies theorem, our theorem square, by doing induction. We can do induction on K. So it's easy to check when K equal to 1 or 2, maybe. So when there, if you have this, so you have this term and you write it down. So let's say the first delta is delta 0, delta 1, delta 2, delta 3. So the last 2 terms is just the proposition tells you. So you only need to consider about the first 2 terms. The second term you use induction. That's the induction. And the first term is it should be automatically 0, right? That's why this is automatically 0, because you can see once you add delta Si means you add the theta zeros increase, get these numbers increase. The number of theta zero gets this number increase. So once you get all these numbers, but you should be, the theta zeros should be at most K. So one time you increase 1 theta 0 or in 1 theta 1. So the total number of theta 0 and theta 1 should increase 1. And you get all this together. So the total number of theta 0 and theta 1 should be equal to K. That's why we don't have a theta 0 can be, the numbers of theta 0 can be K plus 1. This is not possible. So this term is 0 automatically, and the second term is by induction assumption. So now we have this proposition proves the theorem. Okay, now we have to prove this proposition. Okay, so we need more. So this one is this is 2. I think this double I. Okay, double I is exactly the proposition, the determining proposition. But we have the I, so single I. It's a bit different. The difference is because here we allowed the delta to be delta 2 and delta 3, and here we only allowed it to be delta 0 and delta 1. So there's no delta 2, delta 3 here in this inside these brackets. The proposition says that their two statements are equivalent. So now we reduce our proposition circle to show this single KIRK. So it's a different expression. Okay, still not not simpler. Okay, we compute this directly. So you get this special case. So delta 2, delta 0, and this special case. And we use this, then we use the induction again and again. We use this Lie group, Lie brackets to do the commutators. You make all these things into commutators. And still, the statement holds. So you replace this by all the commutators, you still hold. It belongs to D minus 3 times this Chow range. You have to use the induction again and again. So now we get to this operator. So this, now we all have all the replace all these things to be the commutator. So here we just multiply this operator. And once we do this commutator, still we have it, the same statement. It still belongs to D minus 3 times of this Chow range. So the good thing for this operator is it have this property. Very nice ones. You can see you don't have, so once you have all these theta, you don't need to consider about. So you get here. So once you have this SM is belong to D minus 3 times this Chow range, then no matter how many thetas before it, after this operator is still belong to the D minus 3 times the Chow range. That's the proposition diamond. So that's the advantage for this the new operator. Now what we want to prove is proposition circle. Okay, so now we get another expression. So J. So what we want to prove is the IKR acts on some in the Segre integral, Segre class, you get a multiple of D minus 3. Now we get JKRS when it's S equal to 0 is just exactly what we want, IKR. And we use the induction again. We use a lot of inductions, and there are a lot of complicated notations. So it's a bit technical. But it somehow is very geometric, right? So you see this delta, it seems some map, but it comes from geometry. Now that's what we want to prove. And this proves proposition circle. So IKR. Now we define something JKR. And when JKRS, I think JKR, so you have a, we write down this. So it's as is. So what we want IKR acts on this this second integral is into this d minus 3 multiple of secure range. And what we prove is actually the JKR. For all JKR acts on this several classes. So here we have several classes. We don't need to be top several class. That's why we do this, because once you do the pullback and do push forward, you lose some information, right? But when it's top several class, you don't lose too many, okay? But for other several classes, you may lose too much information. Then you finally have a zero, right? But what we prove is for this JKRS, for this complicated operator, so it's very different from our FN, right, at the beginning, but it somehow comes from that FN. So we prove this for this all JKRS. Once you put this operator X on any integral class for this alpha dn, you get something in the Chow range, so of the multiple d minus 3. So the lemma is just say something, some statements equivalent, but what we prove is this. And here, so JKRS, when s equal to 0, is exactly our IKR. So IKR is what we want to prove proposition circle, because so this proposition spade set. So IKR, so the two statements are equivalent. And the first statement is exactly in the proposition circle. So now we have changed the how say our aim again and again, right? So finally, so we can prove this JKRS, the statement on JKRS directly, not very exactly directly, right? That's what we want to prove. So we do the induction on K. So now we have JKRS. So there are three variables. When s equals 0 is IKR. So for K, we do the induction on K. So K equals 0 is obvious, and if you want to, you can check. It's easy to check, right? So now we do the induction. So we prove this equation, and we write it down like, so by definition, that's a definition, right? We have this, and we have this. Here we have this chi-s, this Xs. Xs is what we like. So the Xs, we said, is a very good operator. So once you get this one, this thing here, integral second class here, then no matter how many zetas before it, you always have this. So you can just jump all this and go directly into this this second integral second classes. Okay. Okay, I think that's since we already have. So once you get d minus 3 factors, then no matter how many zetas, how many what operators you act on you, then you always have d minus 3 or factors, right? So you now you get this. So once you have this CS, and you act on this, you can use induction. You show that this acts on this SM. Okay, so we have this proposition, right? We have this statement. Once you have KS on any second class, you get a d minus 3 factor. And by this proposition, no matter how many zetas before this second class, after you act this KZ, you always have this factor d minus 3, right? Since you have this proposition, you will always have d minus 3. And then after that, you add everything together, you still have d minus 3 factors. So that's the statement. So once you appear with, you get once this KC, you have a d minus 3 factors. So JK, so for the J actor, J factor, you act as on any segregable class, you get the D minus 3 factor. In particularly, once you let this IKR. So IKR is a special case for this JKRS. Now we get, so IKR as on any segregable class for this alpha A, D, and you get the factor D minus 3. You get another factor. So now this is a propagation circle. It's our propagation circle, which proves the theorem square, which proves Main theorem. Okay, so I'm sorry that my talk is a bit technical. Okay, so that's my result and my proof.
Okay.
Thank you.
Thank you very much. Yeah. So this is a great computation.
Yes, a bit.
So many formulae. So any question or comments?
Excuse me.
Yes.
At the very beginning, you have a invariant AI in terms of Z. Now you change your naive variable, change your variable into T. It turns out to be the almost polynomial except the square root Y.
Yes. You mean this beginning, right? Their result. Yeah, it seems almost a rational function, but they might be not in integer, right? Almost.
Yeah, I'm asking why only square root arise.
Then you have used the residue formula to do the residue on both sides. And actually what they did is exactly they compute the several numbers. So what the Marian operator Ponte-Panda did is they choose some vector bundle with more deformation space, and they compute this Segre integral. They get exactly, so they get all these the expressions. So you have enough vector bundles with for all ranks you can find one stable vector bundle, I think, with small deformation. So that means that the module space is of dimension 0 or dimension 2. I think this only 2 case they compute all these the Segre integrals and to get they show there the 0 point, the zeros point for these Segre integrals. For some rank they get zeros. And then you since this is a polynomial in R, and once you know enough zeros, you determine this polynomial. You get this expression, but once you want to get exactly this polynomial, right? What's the exact polynomial? You do the residue formula on both sides. You can see this. Actually you can see you do residue on both sides, and you can see what's the formula is not that complicated. It's something not is binomials, I think, not that complicated. I hope this answers your question. Yeah, why they have this the square roots? No, is not exact square roots. Is about the residue formula. You have to do residue on both sides. So to get the term, so to get each term, right? So this is a infinite series. So you put everything together and you do the residue formula. So you have this this expression. You are on case 3, and you don't have this term and this term. So you have the first 3 terms, and you do residue on both sides. So then you have this formula. Yeah, it should, how to say, it's very, I don't know how they get this formula at first, a priori, how they get this formula. Since once you get this formula, it's not difficult to check. right? You got this formula and put everything together and you compute the residue. But why you a priori to get this formula? I don't quite know why they get this. It seems from the paper, they first have this formula and they prove it by showing that they're equal, right? They're equal. So it's showing that from the formula you get the circular integral, and you compute the circular integral is exactly that, the polynomial, right? You have this here, this should be a polynomial, and you compute the polynomial is exactly this one, then you get the answer, right?
Okay, more question? So I've got a question. So this was computed on PP2. So so for other simple surface like root surface or K3 or a building surface, is that possible to
compute
what's
directly?
difficulty?
I think there's a problem that's here. We use this form. I just mentioned what I talked about, but so now once we use the recursion formula, we need this exact sequence. So here we need this structure sheaf of this orthogonal in S times S. So if S is some other surface, you may not have a very good expression for this orthogonal, the structure sheaf of orthogonal. So as we have on S is P2, then we have this exact sequence. Now, and we can compute the term polynomial of this structure sheaf of this orthogonal. And not orthogonal, this is a diagonal, sorry. So the diagonal. So if S is any other surface, maybe, I don't know, I think root surface. Maybe you still have something for this orthogonal, but yeah, but it's totally different, right? So you get the totally different chain polynomial. Then you should, maybe you have a very different you have a very different thing. You have to compute it in another way. I don't know. But here, if you want to compute other chain polynomial, I don't know, if you want, maybe you can use this strategy to compute for P2 case, for rank 0 case. And if you don't circle class, maybe the intersection of other circle classes, not the top, only the top circle classes. I think maybe it will also work for, so not only in compute the top circle class. So if you have, as long as you have something that 0 dimension, otherwise you will lose the information. And my statement actually is not only for the top circle class. For any other circle class, we have also have some statement, but that is you do this F again and again, and then you get 0. But it won't give you enough information, since the other circle classes there have some higher dimensional things, and once you do this pull back and push forward, then you lose those information.
Okay, thank you very much. And due to maybe time limit, so we don't have more time to ask a question. And so let's thank Yao Yuan for the nice talk. So we will resume in 6 minutes.
Okay, thank you for the invitation.